Hello, and welcome to the SimScale webinar on optimizing fanless cooling in industrial computing hardware. My name is Dr. Nagman Khan. I'm from the marketing team at SimScale, and I'd like to welcome you all to this live event. Absolutely delighted to be joined by one of our guest speakers from a long-standing customer, OnLogic, and our guest speaker joining us today is Eric Kopf. Eric, hi, how are you? Thanks so much for joining.
Hi, it's nice to be here. Thanks for having me today. I'm looking forward to having a great chat.
Likewise, Eric. We've been trying to get this webinar done for a while now, so really appreciate you joining us today and your time. We're gonna jump straight in. Eric, we have a super interesting topic here, right? Optimizing fanless cooling in industrial computing hardware. I guess the first question is, why are we talking about this topic? I mean, it looks and sounds super interesting. How important is it, and what does it mean to you and OnLogic?
Yeah, I appreciate the question. OnLogic has been doing fanless cooling for over a decade, and it's something that, while seeming very simple at first glance, has a lot of complexity inherent to it, especially when you're designing for industrial and rugged environments. So I'm hoping to get into that a little bit today, share some insights about things that we're thinking about when we're designing our computers for those environments, and where those really come into play when you are designing your thermal solution.
Fantastic. And a reminder to our attendees, you can use the question panel in GoToWebinar. Please keep posting your questions and we'll pick Eric's brains towards the end of the webinar. Okay, there's also a chat functionality. If you're having any audio visual issues, please use the questions panel to post questions to Eric. So what are we doing today? Here's a quick look at the agenda. I'm going to quickly introduce SimScale for those of you who are new to us. Then I'm going to hand over to Eric, and after that we'll have some Q&A, and we'll end with some quick next steps. You know, if you want to try SimScale yourself, how to jump in and do that. Now, interesting thing about SimScale, we just surpassed 500,000 users globally. So this is a milestone movement and moment for SimScale. So what is SimScale really? It's a next generation cloud native engineering simulation platform. Okay, so we have lots of different types of physics available to you in a web browser. That's what cloud native means. So there's no VPN, no remote desktop, no hardware. It's a true SaaS with instant access anywhere. Okay, we have one platform, the broad range of physics available from CFD, thermal, structural, and our most recently released one was electromagnetics. Okay, because we're cloud-based and cloud native, we have some real-time collaboration and support measures built in there. And Eric will talk about his use of SimScale a bit later on. And recently, you would have seen since October last year, we have some AI-powered features. And we actually have a webinar happening tomorrow night, right, on something called Simulation Copilot using AI features in SimScale. So feel free to go to our website and sign up to that webinar. That's happening tomorrow night, okay? And there's no limit really to simulation size, number of parallel simulations, and storage. Okay, so you can scale up usage of SimScale across teams distributed globally, and also the amount of simulations and the complexity of the models you use. And here's the examples of the different types of physics I mentioned earlier. So on the top left, flow CFD is integrated into SimScale. There's multiple solvers there. Thermal on the top right. We have structural FEA applications on the bottom left, and our recently released one, electromagnetics. Now it's one platform, so you'll see there's a common environment, one CAD model, and you can go through and do these different types of analysis. But enough about SimScale for now. Let's take a look and hear from OnLogic on how they've applied not just SimScale, but simulation in general in terms of their design. Eric, I'm going to mute myself and make you presenter and hand over to you. Thank you.
Thank you for joining this morning. My name is Eric Kopf. I'm a mechanical design engineer here at OnLogic. We are an industrial and rugged computing company based out of Burlington, Vermont. And my goal today is, as I stated just slightly earlier, to talk about some of the gotchas, some of the interesting things that we take into consideration, and some of the reasons why we use SimScale when designing our thermal solutions and industrial computers. So basically how I want to go about this is I'm going to start by talking a little bit about our company to help set the stage, go into some of the thermodynamics of how our computers are working, how we set those simulations up, and then things that we look for when we are going through our simulations. So a little bit about OnLogic. As I stated, we have been doing fanless cooling for over a decade, based out of Burlington, Vermont, but we are a worldwide company. We've shipped over 600,000 systems and have over 250 employees globally. We have computers that are ready to go into a number of different environments, a number of different countries, and basically are here to help our customers get computers wherever they need to access data, collect data, do compute, you name it. Now, the computers that we deal with fall into a number of different categories. And the reason why I bring this up is because anytime that I'm going to be discussing our computers in this webinar, I'm going to be talking about our fanless computers in our industrial and rugged lines. Anytime we're designing a computer to go in a rugged environment, which generally means high shock and vibration, wide power input, high operating temperature, we want to reduce the amount of moving parts that could potentially fail. And when we're doing that, we need to consider how we're removing heat from the system. The reason why this is important is because it creates and puts us in a situation where we are doing what's called passive cooling. We cannot count on there being airflow over our heat sink. We cannot count on having access to cool, clean air or dry air for that matter. So, how does this play into our product design philosophy? Well, as I mentioned earlier, anything in our industrial and rugged line is most likely going to be fanless. This means that we have to dissipate the heat generated by the computer with the shell of the computer itself. That's why you'll see large heat sinks on the top of a lot of our computers. These generally are going to be made of aluminum and are going to be used to get rid of any heat the computer is making. We also have a philosophy of creating highly flexible systems that can meet a number of our customers' needs within a small form factor. To do this, we offer modularity within our computers that also needs to be taken into account when we are doing our thermal design, because we don't just have one part of a computer that's putting off a large portion of the heat. We have many. Now, when it comes to natural convection and removing heat from a fin, the equation really is already solved. There's a number of online calculators, equations, and back of the notepad calculations that can get you the answer to the question very quickly: how big does my heat sink need to be in order to remove heat being generated? Now, why are we having this webinar, you might ask then? Well, like many things, the devil is in the details when it comes to these sorts of designs. If you're a mechanical engineer or a thermal engineer or even electrical engineer on this call, or any sort of product designer for that matter, you know that no one feature exists in a vacuum. Along with getting rid of the thermals generated by the computer, as a design team, we're also dealing with product size and performance expectations, any shock and vibration that we might be setting the system up to take. We also have to consider electromagnetic interference, electrostatic discharge, and specific mounting considerations for product lines that we might be bringing to market. And then at the end of the day, there's also any cost associated with the actual product. And with all of these things combined, the answer for how you remove heat from a system and how much heat sink, how big the fins are, how close the fins are to critical components, that question becomes very complicated very quickly. And because of that, I want to break down industrial computers to their very core and build out from there. So, as I stated, much like equations for natural convection, the thermodynamics of industrial PCs are pretty simple. Like anything, the amount of energy that goes into the system must be removed by the system. If the energy goes up, so must the energy removed. For computers, the energy going into the system comes from the wall. Wherever you're getting power for the system, some amount of current is going into the computer and being used to do the functions of the computer that you're asking of it. And like I stated, with OnLogic's computers, in our passively cooled environment, any efficiency loss needs to be removed by the heatsink. Now, what does this look like in practice? The heatsink of the computer is not just removing the heat generated by the CPU, the central processing unit. There's also the power distribution losses that you might experience in high wattage environments. There are higher and higher current requirements on M.2 and all sorts of motherboard expansion that must be considered. And on top of that, there's also efficiency loss on capacitors, all sorts of chipsets and LAN controllers that must also be kept under critical temperatures for our regulatory requirements. So how do we iterate and use SimScale to solve these problems? Our company uses SolidWorks as our CAD software, but your company might use something different. Really, the icon on the left here, standing for SolidWorks, doesn't really matter. We use our CAD software of choice to develop models based on existing platforms that we know have worked in the past. Based on the new product requirements, we then make small changes to the design that we think are going to cause us to differentiate ourselves, and then put that model into SimScale where we test to see the results, and then from there make more changes. Like any good scientist, we try to minimize the amount of changes we're making on any iteration. We also try to document our results as best as we can and check and see constantly whether our hypotheses are being proved correct. So that way we can make more educated decisions on the next iteration. When it comes to identifying opportunities in our simulations, there are some key things that OnLogic has learned to look for that we use SimScale for when making these decisions about how to create more and more innovative designs. The first thing has to do with heatsink efficiency. Like I mentioned, the goal of the heatsink on the OnLogic computer is to get the heat away from the system. When you are doing this, you want to minimize the difference in temperature across the heatsink. What this means when you have a low difference in temperature is your heat is being removed efficiently. So as you can see in the picture in the upper right-hand corner of the screen, there's a bullseye right over the center of the computer where our hottest component is living. The temperature gradient then goes down to the edge of the computer. This is an example of a result that we saw and we said we can do better on. By lowering the difference in temperature across the heatsink, we are able to more efficiently remove heat from the system. This ethos also continues to the inside of the computer, where we're able to simulate results of internal component temperatures as well. The picture on the left shows some critical components that the OnLogic team was very concerned about overheating on our new product. And by using SimScale simulations, we were able to assign different temperatures to, not different temperatures, my apologies, different materials to these components, different wattages of power they were producing, and then measure the temperatures we were expecting to see once we got our first round of prototypes. A lot of these things that we're constantly looking at when we are doing these simulations are also feeding into other parts of our organization. As a mechanical engineer, I'm constantly talking with our suppliers about how our manufacturing process can better serve our company. And one thing that a lot of these simulations lead to are conversations about different and new manufacturing processes that we might want to use in order to create better performance for our customers. We are also talking about how these results impact not just the performance, but the reliability of our components. In the bottom right of the screen, you can see a CFD simulation of some of the airflow and temperature around the system. By simulating the airflow around and over our system, we can make sure that due to hotspots and different things going on inside of our system, we are getting the best airflow over our natural convection-based heat sink possible. Now, when I say airflow, I don't mean forced airflow. I mean airflow that's generated by the chimney effect created by hot air moving off of the heat sink. Now, how do we look at our results and get the best information we can from them? Some things that the OnLogic team uses when we're talking about these things in our day-to-day meetings is, first of all, what question are we trying to answer before we even run a simulation? And once I run that simulation, am I getting the results I'm expecting? Are the results not what I'm expecting? Why? And what information do I need to be able to answer any questions that might come up from the results? These things can indicate what our next test might be. And after all that, we constantly are also asking who is looking at this information. If I'm looking at the information as a mechanical engineer, I might need something different than our electrical engineers might need. So when I'm interfacing with them, I need to post-process results in a slightly different way. All of this has been really amazing when using SimScale. Finally, what does the information tell me? Am I done? Have we reached our goal? Or do we need to continue to iterate? Now, one thing that I asked before we started using SimScale over half a decade ago was, why do we want to use SimScale? Well, as a company, OnLogic is constantly looking for ways to reduce our overhead IT infrastructure. And if anybody's used thermal simulation software on a different platform that's not cloud-based, they'll know that it takes a pretty beefy computer in order to run some of the current gen simulators. And for me, at OnLogic, finding a way to offload that and reduce the amount of IT overhead that we are using on a daily basis to support our engineering department was something that was very, very advantageous to us. Furthermore, it allows us to access our work remotely. If I'm stuck at home for the day, I live in Burlington, Vermont. We get snowstorms all the time. If I am stuck at home waiting for the snowplows to come by and clean our streets off, I am able to still get access to my simulation runs on my laptop at home and create new runs. Furthermore, when I get stuck, SimScale's technical resource department has been incredibly helpful. I cannot stress this enough, and I can firmly say that we would not be where we are as a company today without SimScale's technical resources and user feedback. We are able to do what we're able to do because SimScale is able to help us do it. Now, that's all that I have prepared for today. I hope that was helpful in some way. I'm sure there are going to be questions. So I'd like to give the time back to the rest of the team and begin the Q&A section.
Great, thanks so much. Let me just switch back to the slides and we'll get cracking on, thank you, Eric, on the Q&A session. Okay, fantastic. Eric, thank you so much for a very, very clear, very concise, and very articulate presentation uh, with the context and how you use SimScale and simulation and the general wider background to your company. We do have some questions, so I'm going to jump straight in, Eric. Okay, and we'll try and take as many as we can in the next kind of six or 7 minutes. If there's any questions we can't answer, we're happy to include some additional resources or responses in the follow-up email. And you will get a recording of this webinar in the next few days once we've had a chance to process the video. So, Eric, I think what would be fantastic to get started with is you and I were talking earlier about the types of markets that industrial computers serve, right? And you might not have heard of OnLogic, but you've definitely interacted with it somehow. Perhaps just give a little idea to our attendees about where your industrial computers can be found in kind of everyday life.
Yeah, I appreciate the question. And I think that is a great segue to talk about, some of the ways that we are designing to meet certain markets and where that also continues to play into the thermal design, which I think is really at the core of what I want to talk about. So yeah, as a company, OnLogic services a number of markets, but really what it comes down to is anywhere you want to collect data, use data, store data, we are there. And especially when it's in an environment where a normal computer is just not going to cut it. So some examples of that are manufacturing facilities, utility spaces such as wind turbine farms, solar arrays, power plants of all shapes and sizes, as well as buildings and in building automation. And so in each of these environments, there's something slightly different that we need to take into account that the user and the design is really tailored towards. For high EMC and ESD environments, we really do a lot to help protect the core of the computer against any sort of damage that it might receive from whether it's power input, lightning strikes, or just bad power. And what this means is we're unable to have these fans or any sort of moving part that would be easily damaged by those things. And because of that, we really need to make the computer its own ecosystem that is sealed off as best we can from the rest of the world.
Brilliant. Mark, related to going into thermal design a bit more now, you meant
Sure.
there was a slide earlier. One of the attendees is asking about when do you what's the limit of fanless cooling? Like when would it be? How do you figure that out and to switch maybe
Yeah.
to active cooling? Yeah.
That's a great question. And the question of how far we can go with fanless cooling is really a matter of how much area and space you have to do the cooling. And during my presentation, when I talked about some of the considerations, the top bullet was actually size and performance expectations. So a lot of the times we are constrained by the size of the computer we can give to the customer. Customers don't exactly want a computer the size of a coffee table, but even if they did, the situation arises where the larger the heat sink you create, the larger the difference in temperature is going to be from the center to the edge of that computer. And if you remember, we were talking about heatsink efficiency. Because we have a large difference in temperature, that means we aren't utilizing the heatsink in a way that's most efficient. There's an opportunity for the edge of that heatsink to be hotter, you know? And so the question moves from how big of a heatsink can I get to how do I efficiently move heat to the edges of the heatsink and spread the heat out. And there's a lot of things we can do there's a lot of mechanisms you can do to improve the resistance to conduction through a heatsink. You can increase the cross-sectional area of that heatsink so that way the pathway of the heat becomes larger. You can also improve the thermal conductivity of the heatsink. So to answer your question, the capacity of natural convection is purely based on the size of the heatsink you have available to you and the efficiency of that heatsink. If you can move the heat, then you can get rid of it.
Yeah. Eric, a related question on the fanless cooling,
Yeah.
but you showed some images of rugged computers, right? That might be used in extreme or somewhat extreme environments where you might have ingress of dust, particles, things like that. Do you have filters before at the air intakes, and how do you model them, the pressure drop across potential filters?
Yeah, great question. So the way that we design our fanless computers is we're constantly thinking about ingress into the enclosure of the computer itself, but and we essentially design our computers in a way that prevents air from getting in. Dust particulate can still get in over prolonged periods of time. These are not IP60 computers per se, but we do design in a way that meets IP40 and sometimes, depending on the computer, IP50 standards. The question I think that's great to ask is how do we make sure that we are setting up our customer to succeed in their enclosure? And as somebody in the space who has a lot of experience with dealing with rugged and industrial cooling, a lot of the times our conversation becomes, hey, customer, we see what you're trying to do here. Here are some suggestions for your enclosure that our system is going in that might make the rest of your, whether it be DACs, whether it be other modules they might be using, that might extend the lifespan of those computers.
Yeah.
That's really what our conversation turns into a lot of the time.
Fantastic. We've got a related question, so I'll take that first, and then I'll come back to some of the other questions being posted. We do have a lot of questions, Eric, which is great to see that audience participation. So you mentioned about the customers, right? We have an attendee asking about modeling one of your units inside a cabinet where there might be other equipment that impacts the thermal performance of your unit. Is that something you've looked at before? You're ever asked to by your customers when they're designing, the whole cabinets and rack servers, things like this?
Yeah, that's an awesome question. And because I know we have a lot of questions in the queue, I'll try to keep this short. The potential installation environments for our computers is almost infinite. And in that, we a lot of the times are actually working with our customers, and we give as much information as we can to our customers about what they can expect from our computers. And more often than not, what we are sort of doing is acting in a way that's sort of supporting them as well as we can. We have different prototyping processes that help our customers get one of our systems, so that way they can just test the performance in their environment. But we also give them CAD models every now and then that let them do some of that simulation themselves as well. We have very good information about how much heat our systems should be putting off and what sort of environment you should put it in. And from there, generally our customers take that information and use it for their specific installation.
Fantastic. I'm going to cluster a few of the questions together because they're overlapping topics. So we'll take two more. So the first one is, we've had several people ask this. Do you have data where you might have tested the thermal performance of your units in a laboratory environment, and you've tried to compare that to simulation results to kind of validate or calibrate your simulations at all?
Yeah, and this is actually a great question and one that I love to talk about. A really important part of our development process that I didn't get into is testing actual prototypes and constantly creating a feedback loop that helps our team understand what sort of and correlate what sort of performance we should expect based on thermal simulations that we're doing. You can spend hours and hours and hours and hours and hours setting up the best thermal simulation possible. But at the end of the day, you want to make sure that that you're getting the bang for your buck that you need, and B, that it's actually correlating to performance. So we have a thermal chamber on site here in our Vermont office, and generally speaking, we use our thermal simulations for our feasibility studies very early on. And then based on our amount of effort that we're putting in to do our thermal simulations early on, we get a level of confidence that we are happy with to move forward to our prototyping phases, where we then validate on actual hardware that we're getting the results we want. Generally, what we see is we have a very close coordination and correlation between performance of our simulations and our computers in our thermal chamber that we have. Then that information gets fed into the next project, where we're constantly figuring out and actually minimizing the amount of effort that we need to put into SimScale to get the information we need to correlate to our performance in the real world, if that makes sense. Our goal as a team is actually to minimize the amount of time we're spending in SimScale, because for any company, time is money. And one thing we found that I actually forgot to mention with SimScale is the amount of time we need to put in to get the information out we need is incredibly low.
Fantastic. It's great design philosophy. It fits in with what simulation, what some SimScale also proposes, to use simulation earlier on in the design process, right? And the fact that you've got this kind of triangulation of simulation, physical tests, lab tests, and monitoring of real life units is, it's really great to see. Eric, we have one more. I'm going to take one more question. It goes back to the example of the heat sinks you showed earlier. So one of the attendees is asking, did you experiment with, and I guess this is a generic question as well, not just on the model you showed, did you experiment with other heatsink geometries and instead of just the parallel bars example that you showed earlier? And how deep do you go into experimenting with different heatsink designs
That's an
as
awesome
opposed to
question.
optimizing? Yeah, different.
Yeah. So first of all, great question. The next answer is that, and it actually kind of comes back to what I was discussing with the considerations that we as a team are constantly dealing with beyond the thermals of the system. So for the most part, a flat plane wall, which is what a single fin on a heat sink is a fairly efficient way of removing heat from a piece of material, in this case, aluminum heatsink. And it's not the most optimal way, but when compared to the manufacturing cost and process and quality expectations of other manufacturing methods and the geometries you would receive, it's the best. What we have found, the heatsink is not necessarily the bottleneck in our thermal design, is what I would say. So we've found that our flat fin heatsink cost to performance is incredible, and we do some stuff under the hood that makes it even the extra mile better. But where we are really focusing, and what I kind of alluded to in my slideshow, was that improving and getting the heat away from critical and hot components within the system is the true crux of the design.
Yeah, absolutely. Eric, listen, thanks so much for sharing all your knowledge, expertise, and experience here, not just in simulation, but in product design, in mechanical design, and being someone who's involved in the R&D side and the manufacturing side. Right? We've really benefited a lot from this expertise, and we'd love to have you come back next year and present again to our audience. I think everyone's found your presentation very, very compelling. So thank you so much, Eric.
Yeah, thank you. I really appreciate being able to come on and talk about what I do every day. It's always fun to do, and as always, it's great talking.
Fantastic. We've already got comments coming in from the audiences. Great webinar, great presentation, Eric. So that's some feedback in real time for you there, Eric. Thank you so
Awesome.
much. And yeah, and to everyone else who's watching, if you're interested in using SimScale, trying SimScale, you can request a one-to-one demo. Uh, Contact us at simscale.com and we'll be in touch with you. We also have a community plan. You can go to our website and sign up to that for free. So thank you so much. And just a final reminder, we will send you a recorded version of this presentation in a few days' time. And we do have a webinar tomorrow at a similar time on our new AI features in SimScale. Thank you for attending and good night.